Hi there, my name is Christopher Worse and welcome to the first video of the Homework 3 for material energy balances. So, obviously, Homework 3 is on your screen here. It's going over material balances with dynamics and control. This video will go over part 1, and the homework's on the screen here. So, the situation is 3 tanks with cross-sectional areas of 0.5, 1, and 2 meters squared respectively are interconnected at their bottoms with initial fluid height levels of 0.5, 1, and 2 meters respectively. The magnitude of the flow between tanks is proportional to the square root of the difference in fluid heights between pairs of tanks, and the proportionality constant between tanks 1 and 2 and tanks 2 and 3 are 0.1 respectively. Tank 3 drains to the surrounding at a height of 0 with the same proportionality constant. So, for part 1, it asks us to derive the differential equations to solve the fluid levels in the 3 tanks. We're only concerned with the first paragraph here. That's what outlines the situation, and it also gives us our equations. So, with that, let's begin drawing out the situation and then writing out some equations. All right, so let's begin by drawing out. I have marks here and here so we can so you can see better. Let's begin by drawing out the situation. So we have 3 tanks with cross-sectional areas. So let's begin by drawing 3 tanks. So we have tank 1, tank 2 is a little bit thicker, and then tank 3 will be a little bit thicker than tank 2. Now these don't have a prescribed height, just the initial height of the liquid inside. So their tops will be open. There's tank 2. And there's tank 3. So, the question says, the tanks are interconnected at their bottoms with initial fluid height levels, which means that liquid can flow between tank 1 and tank 2, and tank 2 and tank 3. So, let's begin. Let's put liquid at height 1 in tank 1, liquid at height 2 in tank 2, and liquid at height 3 in tank 3. Now, the values are given in the problem, but the values aren't important right now. And tank 3 drains to the surrounding at a height of 0 with the same proportionality constant. So, tank 3 here drains out to the surrounding area. Does it say where? Yes. The flow into the second tank is set equal to a proportionality constant multiplied by the difference between the fluid level set point for the third tank and its actual fluid level. So I was wrong. The second paragraph is important. It outlines the flow here into the tank. So, now that we have our picture set up, let's begin by drawing writing some equations for it. So, the most important first equation is accumulation of something, liquid in this case, is equal to the liquid coming in minus the liquid coming out minus the liquid consumed. So for the total picture here, we have liquid coming in here, coming into tank 2, and then liquid coming out of tank 3. Consumed is a non-factor, we don't have to worry about that. But the important thing is that the individual tanks here also have accumulation of their own. So the accumulation of tank 1 is different from the accumulation of tank 2, is different from the accumulation in tank 3. So let's begin by just writing out what the flow rate should be between them. So the magnitude of the flow between tanks is proportional to the square root of the difference in fluid heights between pairs of tanks. And then the proportionality constant between tanks 1 and 2 and tanks 2 and 3 are a value. So we're going to name the flow rate Q. So Q, the flow rate between tanks 1 and 2, is equal to, I'm going to switch markers. Go. Yeah. All right. The flow rate between tanks 1 and 2 is equal to the height, yes, square root of the height. So square root of the height of tank 1, so height 1 minus height 2, tank 2, square root. Now, what happens if height 2 is bigger than height 1? Well, that means we have a square root of a negative and we don't want I. So we're not going to have that. So I'm just going to use the square root of the absolute value. We also want the proportionality constant, which we're going to name alpha, of alpha 1. So that should be all we're done. The flow rate should be good. But what happens if height 1 is greater than height 2? That means that the liquid is going to flow towards tank 2. And if tank 2 is more full than tank 1, then tank 2 is going to flow to tank 1. So there needs to be a way to change this, because this will be positive no matter what. So we're going to put multiplied by the sine of height 1 minus height 2. Multiplied by that means that if tank 1 is more full than tank 2, this entire thing will be positive because it will flow to tank 2. And then if tank 2 is more full than tank 1, this entire thing will be negative because sine is negative. That means this is going to flow to tank 1. So we've basically just assigned a flow direction as positive or negative. So we're going to do the same things for tank 2, for the flow rate of tank 2 and the flow rate of tank 3, which is also the flow rate out. So the flow rate from 2 to 3 is equal to basically the same thing. Now I'm going to rewrite this because I like the way it looks better. So again, this is the sine from tank 2 and minus tank 3. So again, if tank 2 is bigger, then this will be the positive flow rate is towards tank 3. The negative flow rate is from tank 3 to tank 2, times the proportionality constant of tank 2, times the times the square root of the absolute value of height 2 minus height 3. I'm going to rewrite this top equation to match this in terms of setup. Okay, so now we have Q3, or we're going to call it Q out, because that's what it is. It's the flow rate out of the system. And that said here is surrounding height of 0 with the same proportionality constant. So it's real simple. Sign is no longer an issue. This absolute value is no longer an issue. We simply want the proportionality constant of tank 3 and the square root of the height of tank 3, of the height of the liquid in tank 3. So with that, we can set up our accumulation here. Almost forgot. We have one last flow rate. We have flow rate in, which here is set up as the proportionality constant multiplied by the difference between the fluid level set point for the third tank and its actual fluid level. So the flow rate in is equal to the proportionality constant, labeled as Kc in this equation, multiplied by the set point of height 3, what we want our the height of the liquid in tank 3 to be, minus height 3, its actual height. So now with that we have all four. Now we can actually set up an accumulation system. So accumulation is equal to in minus out. So we're going to write three things of accumulation, one for each of them. Now, first to define what accumulation is, well, accumulation is, in this equation, in this scenario specifically, it's the change in height. Since the cross-sectional area is the same, it's the change in height, but that's represented by change in volume. So, it is going to, if volume is, in here, area times height, it's going to be area 1, times the derivative of height, so dH over dt as the change rate in height, is equal to here. Well, we really only have one here. It is, if it's going this way, dH over dt should be equal to, we have 1 and 2, we want it to be negative specifically. So the accumulation is equal to the negative of the flow rate from 1 to 2. That is because if the height 1 minus the height 2, if the liquid in tank 1 is greater than tank 2, that means that liquid is going to be flowing out of tank 1. So if Q is positive, that means accumulation has to be negative. So we have our accumulation set up for tank 1. Let's do it on tank 2. So again, the area of tank 2 times the change in the height of the second tank. I added the 1 to denote that it is height 1. And then the derivative is equal to, now there are three things here. So if if the flow rate of Q1 to 2 is negative here, it should be positive because it's part of the in. Also, the full flow rate in is part of the in, and then out is the flow rate from 2 to 3. So let's put flow rate in so flow rate in is equal to proportionality constant times the set point of tank 3 minus the height of the liquid in tank 3. So we have that here. Plus Q1 and 2. Actually, I'm just going to write it out. plus the flow rate from 1 to 2 minus the flow rate from 2 to 3. That's our accumulation here. Finally, let's do our accumulation for tank 3. So, same left side general setup, the cross-sectional area of tank 3 times the change in the height of the liquid in tank 3 is equal to, well, if the flow rate from 2 to 3 is negative in tank 2, it must be positive in tank 3. So that's in. And then liquid is always draining out, so the flow rate of Q out is always the out in accumulation. And with that, we have all of the data, the equations that we need. We have 3 equations and 3 variables. We're looking for the change in height 1, 2, and 3. And in the problem, we have our values for them to use. Thank you very much for watching, and we'll get right to coding this.